All right, so we'll prove that Q is dense in R. So what does that mean? That means that for any two A and B in R, we assume A is less than B, then we can find an element of Q that exists C in Q such that C is an element of this A and B. In other words, A is less than C is less than B. I'll use R. Okay, so we'll find a rational number R that's between A and B. If R is like M over N, then we're going to be looking for a rational number between M over N between A and B. So what we will do is we're going to do, so 0 is here. Let's say A and B are here. Okay, we're going to measure the distance from A to B. That's B minus A. And we'll pick a natural number n such that 1 over n is less than B minus A. So this 1 over n is smaller than B minus A. So it's kind of like 1 over n is this wide, perhaps. Okay, so then we start with 1 over n and take steps each 1 over n wide. So 1 over n, 2 over n, 3 over n, 4 over n, and so forth. So eventually, we will land here just a bit less than A or maybe at A. Then the next one, M over N, will be definitely between A and B. That's the idea. That's what we want to do. Okay? So let's see. So let's erase all of this and I'll formalize our proof. Okay? All right. Also, if we can do it for the positive A and B, we sure can do it for negative A and B, okay? So suppose A and B are in just real numbers with A less than B, okay? So if B is less than 0, what I'm thinking is 0 is here, B is here, and A is here. We can look for minus B and minus A. Find, if we can do for positives, then we'll be able to find an R between B minus B minus A. Multiply this by minus R will be between A and B. So that's what we want to say, okay? If B is less than 0, then we will find R in the interval minus B minus A. Then minus R will be in the interval AB, okay? Where R is a rational number. So we'll find an R. So suppose now B is positive, okay? So remember what we did with, we want to get M over N less than B and greater than A, meaning that NA less than M less than NB. So we'll work with this side. We'll see if we can find an M right up against B, okay? So that's what we're going to do. So we'll build a set and see if we can find the one element M that's just next to NB. So suppose B is greater than 0. By Archimedean principle, let n be a natural number such that 1 over n is less than B minus A. So build a set S. So let S be the set of all k's integer such that k is less than nb. Okay, so there are a few things we can say about this set. The set S is non-empty because 0 is in it. 0 is less than nb. Okay, S is subset of the set of integers because we built that into the construction of S, and S is bounded above. Because we just have an upper bound nb. So it has a maximum element. Any bounded non-empty subset of integers bounded above non-empty subset of integers has a maximum element. We just proved that in the previous. We just proved that in class. So let M be the maximum of S. Okay, so we have two things going. M is less than NB because it's an element of S. Okay, and if you add 1 to it, it is greater than or equal to NB. Likely greater than, but it could be equal to NB. Okay? Well, what does this mean? This means that M over N is less than B. And if you divide by N, M over N plus 1 over N is greater than B. Okay? So I will prove that M over N is actually greater than A also. Okay? I have M over N is less than B. And M over N is less than B. I'm going to be using this trick, this guy, and the fact that 1 over N is less than B minus A to show that M over N is greater than A. Okay, I'll do that in the next page. So now we have M over N less than B done, so I'll start just simply M over N plus 1 over N is greater than or equal to B, and 1 over N is less than B minus A. Let's start with this, okay? So let's add B minus A to M over N. Since B minus A is greater than 1 over N, this is strictly greater than M over N plus 1 over N. Why? This is M over N, and this B minus A is greater than 1 over N. So B minus A is greater than 1 over N. That's by the choice of N. And this is greater than or equal to B because it's just this inequality. I just put that inequality. So that now all of this stuff is strictly greater than B. Okay? So that means M over N plus B minus A strictly greater than B. Okay? What just happened? Something happened. Okay. All right. So subtract B from each side and add A on each side is greater than A. Just B. Subtract B. Move A over. So that means M over N is greater than A. Thus, A is less than M over N, and M over N is less than B, and M over N is a rational number because N was an integer, a natural number, and M was an element of the integers, so M over N is a rational number. Okay? So, therefore, the set Q is dense in R. Okay, so I think I'll stop here and I'll add one more theorem that says the set of irrational numbers is also dense in R. Okay, I'll do that in the next video. It's much shorter than this.